All right, folks, I think we should get started. So waiting a little bit for Peter Jen to join us. Peter will be the main presenter today to walk you through the reference implementation for machine learning.
Good morning, Wintao. I'm here.
Hey, Peter. Good to have you. I was just waiting down a little bit. So I think we should get started. We have a quorum now. So I'm Wintao. So I'm working in the machine learning group. So as you remember, we have sent out a reference implementation email a couple months ago about how you can use that reference implementation to kind of as a template for your own machine learning project. So we promised tech talk, so here we are. Before we get started, I want to run a little bit plug for BDI Tech Talk. So this talk is part of that series. The BDI Tech Talk is for engineers, by engineers, or you can think of engineers as well. The audience is, of course, the whole engineer community, and anyone in the engineer community can present. You don't have to be just from BDI teams. And we want to run that every month. So every time, of course, we're going to run in 2 time slots, one for European and Bangalore area, one for the United States. And topics can be anything that of your technical accomplishment, your project, things you have done, that you feel like the technical perspective of that project can be shared with a broader audience. If you have such topics, then feel free to submit the entry to the wiki here. So here's a wiki link in the slide. I'll share that later on with in the chat window. But if you click on that, you're gonna go to the wiki page in here. As you can see, we have past event and upcoming event, and right now we are in the machine learning reference implementation one, which Peter gonna walk you through. So all the recording are here. If you can't make it somehow, feel free to come to the page to look for recording and get the insight from talkers, from the speakers. Without further ado, I'll pass to Peter. I'm going to walk you through the reference implementation. I'm going to do that right now. If I can find you in the name list, Peter. Where are you? Oh, you're here. There we go. Okay.
All right. Let me find the right window to share. I think this is the one. Okay. Hi, good evening, folks. Well, good afternoon, folks. This is Peter Zheng. Can you guys see my screen? The one with PowerPoint?
We can see the Gmail window. Now with PowerPoint, yes.
All right, good. Let me close the Gmail window. All right, let me put the PowerPoint to the front. Okay. Yep, I think I got it. So yeah, good afternoon, folks. So let's get started. So today we're going to walk through the representation for machine learning. So this project is done quite a while back, and the purpose of we're doing this is a few purposes. You know, we started project with we try to create a simple project to try to use that as an example implementation to show some of the best practice pattern we want to recommend folks to follow. But the primary reason is to also try to find a way to, there's a lot of folks that went through the machine learning everywhere program and went through the Coursera class, right? I think we have quite a lot of people graduated from that. But a lot of folks are not able to get their hand dirty to get some project started yet. So one of the reasons we do this is also to show folks, how can we get something, just start quickly in the context of this organization, find a project that's relevant to our own day-to-day, business problem and do something about it. So this example project try to also show you, what should we put our data, what technology we use, some design patterns. So it's for that purpose. And yeah, so for some of the folks is you guys already I see on the audience you already did quite some machine learning project, so this may not be too suitable for you, but I hope you can stay on and give us your feedback or just comment. So yeah, so we'll start with talking about what we're solving for, and then we do a quick demo of how the model is being used in a demo app. And then we try to get our hand dirty to just go through the project wiki pages, and if time allow, we work through some of the code. For machine learning project, we really don't have that much code, right? So I think we're going to spend quite some time talking about some key challenge that I personally feel will be likely occur for most of the machine learning project. Things like what kind of data we use, how do we identify, how do we know that's the right data, the feature, how do we get a predictive feature out of the raw data we get, and also how do we know the feature is actually relevant to our predicted target state. So I think probably spend a portion of the time talking about the most important part of any machine learning project, which is feature engineering. And hopefully we can save 10 minutes or so for Q&A. And just like any other presentation, anytime if you have questions, comment, feel free to ask on the spot. We don't have to wait until the end of the presentation to do a Q&A. So with that said, let's move on. So yeah, what's the problem? So one of the common problem for many medium products, GoToMeeting included, is the audio feedback and audio echo situation. So this is a kind of annoying. It's not exactly audio quality, from audio engine point of view, right? It is a scenario that happens a lot when you have multiple folks joining the same GoToMeeting in a nearby in the same conference room, for example. And we have a multiple device, have multiple mic or multiple speaker all turned on. They kind of get into a the circling effect, right? They basically the signal got amplified multiple time, and they got this annoying real loud pitch. And we just see that almost on daily, right? There's too many times that we see that, and really there's no solution at this point technically. So it's so basically when we see that the way we are handling this kind of problem today is mostly just telling the folks on the call to mute your call and to mute your mic, and many times they have to turn on the speakers. And for folks who are not quite familiar with this scenario, sometimes they just give up. They don't know what to do about it. So we decided to take a shot at this problem with machine learning, and I'll spend a few minutes on why we're doing this, why we think this is a appropriate problem for machine learning. Because that will hopefully also shed some light to share, so my own finding, to identify a more appropriate business problem that's a good problem for machine learning to solve. So we decided to do this for a few reasons. We look at the problem. We haven't really solved this feedback and echo detection issue in many medium products for a long time. Well, I'm not a digital signal processing engineer, so I couldn't speak too much detail into why we're not doing that. So folks on the call, I think there's quite a few experts on those, so you guys may be chiming to comment on that. But my interpretation is it's probably going to be kind of not so straightforward to handle this, just writing code to deal with all these edge cases, signal processing. The algorithm may be too complicated. Anyway, you don't have it, right? So it's not just GoToMeeting that doesn't have it. Almost all the medium products I know, doesn't solve this problem. But then on the other hand, it's a really obvious problem for a human, right? If you are in the meeting and you hear the feedback or the echo, it's no brainer, right? You can always tell that it is happening. It's for human ears. So there's no ambiguity. This is the kind of problem I call, no ambiguity machine learning problem. While it's difficult to code, to use a coding and a conventional software engineering approach to solve it, it seems pretty straightforward, and for humans to know that it is happening. And that observation prompted me to think that, oh, yeah, this is perfect. This well, not perfect. This is an ideal situation, ideal problem for machine learning, which is machine learning. The way I think a lot of ideal projects for machine learning is that you can't easily solve it in conventional way. But then you have a lot of data that can be, hopefully have a pretty clear pattern established, which can be one way to speak for that is, as human, you can tell it's happening. And if you have a lot of data, then that's perfect, right? Then you can you can establish a model, and you data train it, and hopefully, you have a valid hypothesis right here. So that's why we decided to take this problem as machine learning candidates for representation. And also we're hopeful of, maybe we can do a good job. We can validate our hypothesis and even possibly have a realistic solution for audio engine. We can do something about it, right? If we can have a high confidence detecting the presence of feedback and echo, hopefully we can apply some signal suppressing technology to mitigate that problem. So with that, this slide show you the just typical workflow, the pipeline for any machine learning project. So it started with collecting data. We painstakingly take a lot of effort to collect about 45,000 audio clips. So those are every single these audio clips are 1 second long audio wave audio clips. And it is painstaking effort to do that because we have to manually, we collect some from internet, but like basically these 45,000 audio clips are 3 labels, right? You have the normal sound, the one we collect from a lot of webinar recording, from YouTube recording. Those are easy. You just get it, and there's no feedback, there's no echo in there. It's just beautiful sound. The harder one are those clips that we want to identify as feedback and echo. And those you just have to, there's really no way to, I can't really see those appropriate data. At least a lot of them from internet, like from Kaigo, from some of those well-known data set or website. So we have to create that ourselves. And so what we do is we manually, we create a lot of, we create a situation to generate feedback and echo, and we painstakingly, cut the clips, hopefully with the 1 second as full as possible, contain the feedback sound or the echo sound. And we manually labeled quite a few thousand, a few hours of those kind of data, and it's still not enough. So one thing we did here is that we use some, audio processing software, some tools from Adobe, Audacity, or there's some tools we use to try to augment the data we generated with different way of distortion, and just to get a more a broad collections of the feedback sound and echo sound. So anyway, in the end, we got about 45,000 audio clips that we consider training examples. So that's data collection part, and I will spend quite some time later on now that I collect the data, exactly what kind of machine learning feature we got out of those clips to make it useful for machine learning training. So that is data collection, and then after that we did a lot of research to this is the most important part of a machine learning project, which is feature engineering. So for that, you start with audio clips, which is just the raw data. Actually, let me switch to the next slide, and then we can come back here. So we talk about, we collect this many data. So just a little bit background of this for folks who are maybe not too familiar with audio, the way audio works. So the original audio clips are basically 1 second long sound wave, right? They're continuous analog signals. But we use with digital sampler, the sound wave can be sampled at a particular sampling rate, as a sequence of discrete time signals, or so-called samples. So for example, on the Mac, the original audio waves are sampled with by default 44.1 kilohertz rate, which means for that 1 second clips, you got 44,100 data point. Each data point is a floating point. It's what we call sample data. So that's a lot of data for just 1 second. And if you have a lot of data, your training set simply be too big, and training efficiency and all this. Put aside the accuracy side, right? Just for the sheer side is a pretty big data, and usually if you have a really large feature set, you also need a huge amount of training examples in your set, right? So that's too much. 44,000 I consider is too much. So I'd like to do some sample reduction, and the thinking on this is when you hear the sound, you as a human, right? I experiment with quite a few different variations in a way that obviously you can hear the feedback and echo sound in the being present in the audio when you hear the original one. But I did a sample reduction all the way from 44,000 to to 16,000 to 8,000 to 4,000 to 2,000 to just make it a more coarse grain. And I kind of noticed that for human, just personal experience, right? I kind of noticed that if I go down to 4,000, I have a hard time to just with my own ears to accurately detect, there's a presence of echo or feedback or normal sound. It's like becoming, you lose too much resolution, then you can't really tell anymore. But 16,000, I can tell with confidence, no problem. But with 8,000, I just also no problem. For human ears, I can tell pretty much with confidence that no matter what the situation, the echo is happening, feedback is happening. I can tell that pretty accurately. So again, driven from the human observation, I decided to give it a crack, to try do a sample reduction all the way down from 44,000 to 8,000. This way, I reduced the data set by but the feature, right, by just data size by itself shared by about 80%, right? So from 44,000 down to 8,000. So you use the command with FFmpeg to you can do a sample reduction. Let's go back to that slide. So that's how we started with the raw data. Later on, I'll spend some time. I know that's not enough, but we decided to use we did some research using audio features, which I'll come to that short later. Just to finish up this pipeline talk. So now you get data, then you can create a model, and we basically we use a really pretty cool tool called Data Robot to do really fast iterations on all kind of models and feature selections. So we did a lot of raw discussion evaluation to come up with the right model and the right feature that are that deliver appropriate accuracy as well as efficient. So just to come to a conclusion first, we found out we're using gradient boosted tree. It's a very efficient model for our case, and later on we even did just as part of the hackathon project, we did a quick integration with GoToMeeting audio engine team to see whether how can we use it for real. So yeah, again, jump to the conclusion a bit quick, then we can go back to work through the code. So just to highlight some performance we got for this exercise, we're able to get about about 90% accuracy and to detect the sound to be correctly to be a normal sound or a feedback sound or echo sound. So that is we initial test that we started 60%, which is really pathetic. It's just not going to be good enough. We quickly reached to 80%, and then with some really creative feature engineering using audio features, which we'll talk about later, we eventually cranking up to about 90%, which is pretty cool. Any questions so far? Let me take a pause here. You guys can hear me?
Yeah, I can hear you.
All right, good. All right, I just keep going. So feel free to chime in if you have a question or comment. So yeah, so let's talk about the feature engineer on the using the audio features. Yeah, so as I mentioned early on, we did a sample reduction from 44,000 to 8,000, right? But that's still sample data. That's the original, you know, the the signal intensity, energy that is showing on the, you know, they show the like, waveform of the sound. Um, we actually initially just started with that, you know, with 44,000, with 8,000 sample data as our feature. So you got a feature set with, you got a training example with 8,000 feature right there, you know, sample data. And we did some data robot, you know, we throw that data into this pretty cool tool, machine learning training tool called Data Robot. And we got decent result, you know, it's actually with 8,000, we got, you know, 80 some percent accuracy, which I'm really surprised. But, you know, you can do something even with the raw data, as long as the granularity of the data is not lower than 8,000. But then it's too big, right? It's also training time take a long time. So we did some research. Well, I myself is not a you know, digital signal processing engineer, so it cost me quite some time to do some preliminary study with you know, how this work, and did some paper, you know, read some paper about audio features, and it comes to I realized, and there's a lot of cool use of an audio feature tool for all kind of audio processing. For example, people using audio feature to try to detect a particular sound, whether it's what kind of music that is, right? It's a rock and roll, it's a classic, you know, what kind of music they use. They use audio feature to do that. And these so-called audio features are basically a digital engineer process to using Fourier transformation process to process your raw sample data on a frame by frame basis to generate, to do some transformation to generate some interesting data that are that can predict the certain pattern of the type of the sound. The detail of that I don't really know, but I just, you know, reading through the paper, I realize there's quite a bunch of a collection of audio features that are capable of doing different things. You know, some of them is good at telling you whether this is a conversation, whether whether it's a music, or, you know, some of them it can be used to detect whether, you know, what kind of instrument the sound is played with. Which get my attention. I thought, yeah, this might be useful for you know, detecting the type of sound we're talking about here, which is normal sound, you know, the feedback sound or echo. So and then I came upon with this open source tool called Yafi. It's a yet another audio feature extractor. It's a pretty cool tool that you know, I think out of box they support you know, extracting 29 different kind of audio features. And there's actually a lot more different type of audio features, but with this tool, at least I got 29. And I figure I can use that to give it a try. And a little bit background on this is just for folks to be able to you know, to go along with understanding, you know, how this feature works. You know, every single audio feature itself is a type of feature, and because I mentioned earlier on, they work by frame to do a Fourier transformation to generate additional data out of that. Each frame is about, by default, is 10,024 sample data. So as you can imagine, with 8,000 audio clips, there will be actually generate for each individual audio feature, there will generate a lot of data points. And we're talking about the 29 of them. So the end result is that depending on which audio feature you're talking about, they have different number of data point. But total result, you know, if we actually get all these 29 features and get all the data point for it, there's about 3,300 or so data point. It's a little less than 8,000 we started with, but it's still a lot. And the things that I don't, you know, being a newbie in the digital signal processing, you know, world, I really don't know which feature to use. But here's come to rescue, right? So for machine learning project, you know, one of the things you can do is that you don't have to care, right? You don't have to know which feature is predictive. You can, you know, we're using this wonderful tool, the Data Robot. So I started, you know, I decided to give it a really quick, you know, a crack of, you know, what's happening. Even though I myself cannot tell which feature is predictive, I don't really care. So I just threw all these 3,000 data points extracted out of the 29 audio features, you know, with Yafi, threw into that, you know, labeled with, you know, the type of sound they are, and threw that into Data Robot and did a really quick run of testing. And Data Robot is capable of taking all this data and simultaneously train about 30, 40, 60, I don't even know how many, a lot of different kind of models, algorithm and then they will they show you a leaderboard of that, which I will show you later. You can get an idea which model works well, and you can do a feature impact analysis on those models that you think are doing well, and that's what I did. So after first round of the testing, I did a feature impact analysis, and I found 30 most impactful auto features. These are not the 30 type of auto feature, but 30 data point out of that 3,000 data point, which is very encouraging, right? So I say, oh, maybe I can give a try. I can just test. So I quickly using data robot, same thing, the data without recreating a project. I just handpicked those 30 most impactful auto features and did a retraining on that, and throw away all these other 3,000 or so data points to see whether I can use a much smaller set of the features and achieve a similar result. And it is very encouraging. It's actually not as accurate as all features and all the data I use for good reasons, but it's pretty cool. But then from that study, I realized that I kind of noticed for the 30 data point, a lot of them are belonging to this particular type of auto feature called OBSIR. It stands for octave band signal intensity ratio. So I noticed that like half of the most impactful feature in this category. And so I decided to tell myself, and I noticed that the total about 49 data points for all the OBOs for the total of this number of data points for OBSR auto features. So I say maybe I just use this auto feature only instead of using 30 data points, but spread out into many different other auto features. The reason I'm saying this is it's kind of expensive to extract the auto feature from those 1 second clips. So if I only extract one auto feature called OBSIR, then it's a lot more efficient, right? So again, it's become an efficiency game. So I decided to say, why not just try OBSIR? Because it seemed to me it's contributed half of the data, the most impactful data point, and maybe that would be good enough. So I don't have to waste time to extract the other 28 auto features, which is a really time-consuming process. So I did a try with that, and surprising, with OBSR's 49 data points, the accuracy is really good, and obviously the efficiency is very good because the data point is so small, and because I only extracted one features, the data processing part is also very efficient. So that's the journey we went through, and let me use a tool to show you how do we actually quickly do this. But before we jump to the wiki page and get hand dirty, let me take a pause here again. Any questions so far?
Peter, do you have like a high-level diagram that can describe the architecture probably or the flow?
Yeah, definitely. Let me jump to that. You're asking. So, I mean, this is not a software architecture, right? It's basically a pipeline, and this is similar to the high-level pipeline I showed in the PowerPoint. So we started with the 1 second wave file is a dot wave formatted sample audio clip. We did a sample reduction. We convert that to a mono audio, so single channel audio. So that's the first step, data preparation. And second, we out of this raw data, we apply Yafi to it, and we extracted the OBSR audio features for every single audio clips. We did some data cleaning to remove some, some clips, the corrupted and the missing data, whatever. There's just necessary cleaning to remove data you don't want it. And from there, we generate the training set. It's a CSV file with about 40,000. Actually, we did the training with 20,000. Later on, we do the echo detection. We had another 20,000. It's 45,000. But for the wiki page, you see, I'm describing this 20,000, 24,000, training examples. And from there, I threw into the data robot and did a lot of iteration to come up with the right model. And then from there, once I know which model I wanted, the model score, I figured that's the good one. Then we decided to say, because one of the problems with data robot is that they don't quite want to export the model they train for you. But we actually want to do this experimentation by getting the model out and to embed that into Auto Engine or into our sample app. So what we do is that now that we know which algorithm we use, which is a gradient boosted tree, then it's easier, right? We just go to we pick the popular Python package called scikit learn and use the gradient boost tree implementation from that package and hand code that algorithm myself, which is pretty straightforward. Because that's writing code for machine learning product is always the easy part, right? It's always doesn't take much time. It's always the data selection, data research, and training and evaluation is taking 99% of the time. So after we code it and we got the actual model, we export that into our sample application. We got even a C++ implementation of the same model and export that into auto engines for auto engine integration. So I guess that's the architecture. So does this answer your question?
Yes, thanks.
Okay, any other questions, folks? Okay, you guys are very quiet. Let me keep going. That's all right. Feel free to to chime in when you have questions. Okay, so yeah, let's jump into the wiki page. Okay, we're down the PowerPoint part site. So so we put a pretty detailed wiki page to tell you where the project is, where's the data. The primary purpose of the wiki page is to for folks, if you want to replay this project on your desktop, it should be easy for you to do so. And one of the message I want to pass around is that I kind of noticed a lot of our machine learning effort. So we have some limited effort so far. It's very difficult for folks to go in there and chime in or see what's going on and experiment with it or maybe suggest for improvement, because it's difficult to get it working on your own computer and replay it. And my observation here is that unlike any software engineer, there's really not that much code, right? Most of the machine learning project is a bulk load of the code is actually data processing script. The model itself is really not that much. Usually we use a lot of this already made algorithm on the street, with the scikit learn library from Python or with Spark ML. You don't really write those the algorithm from scratch. So there's really not that much code. So but the observation here for machine learning, is really the data, right? The data is the one data is basically the code. So, but a lot of because it's not the same as the many conventional software engineer development process. So you don't have so most people don't check. For example, you don't check in your data, right? So you don't have data really there. So I go to your Bitbucket and download the code. I don't know what to do with it. I don't have the data. I don't have the features. Really can't replay your project, right? So we come up with a machine learning development guideline to try to see, to encourage folks to follow, for the purpose of to make your project more transparent and easier for other people to contribute, to learn from your effort, to contribute your effort, right? To all this, the kind of a software engineer, the SDLC process we follow for conventional software engineering process, which benefit the entire industry, right? Everybody follow that. It's no brainer. So we suggest people to, of course, checking your code into Bitbucket instead of just in your RStudio or Python Studio. That's, other people can't see it. And more importantly, checking your data processing script, because after all, that's actually the most of the effort, right? To really show people how you get data prepared. And also for each project, I have a README file to describe how to get on board. Of course, just usual stuff. And also, very importantly, have your data in the, the data is the code. So have your data in the data lake. And for the sake of easier onboarding folks, put a maybe the Bitbucket is not appropriate to store a large amount of data, but put a portion, like a downsampled set of data in the data set directory, just so people can actually out of box use the data and your script to start training, right? So get people onboarded quickly. So yeah, place your script and data scripting in the source directory, and then put your trained model and a serialized model in the model directory, so people know how to play with them. So it's just a very basic guideline, nothing fancy here. And the important thing is to put your data, right? Make your data available. I mean, I know for a real project, your data is always changing, right? You have a new fact, new observation from production. So you have a production system to support your data. But nonetheless, for people to be able to get a clue of what the training is about, what you're solving, and also give them a chance to contribute to your project. You want to put a decent size of the data in the what do we call LMI machine learning data set. Document your data set on those wiki pages, and make your data available in the machine learning data set, which is a bucket under the AWS S3. We have a special S3 bucket just for the as a central location to store all the machine learning projects. So this way, and you document that, then any people can come here and get your data and get your code and start training about it, right? So that's actually how you can engage people, and we like to encourage folks to think about that when you do your machine learning project. Always think about how you easily get other people to work on your product without even spending too much time telling them how to do it, right? So that's the purpose, and that's the objective. And one thing I want to mention also is that one of the tool we benefit a lot, which is Data Robot. As I mentioned early on, this is a tool we use a lot for really quick experimentation for models for data and feature engineers. And if you need a license, if you want to get access to that, you can send an email to Andrew.greenhut at logmein.com for access. So any question on this on the guideline side? Okay, no question. I just keep going. So, okay, where are we now? Where's the page? Okay, so back to the wiki page. So that's a quick touch point on the guideline side. And so let's see how we work with this project. So there's a README file. I put a link on the wiki page, which is right here. So this is actually under the Bitbucket, at the root directory. And one thing I want to walk you through is that so there's a few dependencies this project needs, but not much. It's basically the Python. We use Python for data scripting development and for creating the model. Yafi, what I mentioned earlier on, is the tool we use to do data processing. We got the raw sample data, AutoCAD is not much use. So we use this tool to generate the features we actually wanted to create to do it for the model, for train the model. And FFmpeg is for sample reduction. So it's pretty easy installation, except for Yafi is a slightly, for folks who are brave enough to actually test it, right? You want to get your hand dirty to experiment with this project. I just will tell you that it's a little bit tedious to set up Yafi because it's not a straightforward installation process. You have to download the code from the GitHub, the public repository on GitHub, and do a build. But this wiki page gives you a quite detailed instruction on how do you get it installed on your environment. It's pretty easy for Mac. For Windows, you have to follow some of the details. Some of the specific instruction here is a slightly challenge. Basically, the challenge is you have to make sure you got your Python package into the appropriate directory to make it usable. So just follow the page. Yeah, you should be able to get it going. And for Linux, it's also like non-Mac, not a Mac, right? But just a regular Linux box. It's also you have to go through. There may be some hurdles you have to go through, but we tested it. It's working for all these different platforms. So get a Yafi running, get a Python, get a FFmpeg, then you're way to go. You got your code from here, as you can see from the page. So let's back to the wiki page. So with the code and the prerequisite download, you should be able to get it started. And yeah, this part we can skip it. We already talked about. We spent quite some time on how the data is prepared. How do we make it efficient? Feature engineering, we talk about it. And okay, one thing I want to mention here. So the auto feature I mentioned, they have a lot of data points, and as you can see here, I'm just showing you for OBSR feature alone, we're about 49 data, and each data we just give them different name, _0, _1, all the way down. Oh, actually more than 49. There's 100 something. Yeah, there's actually 112. Yeah, sorry, for 1 second, is 112 data point, not 49. Yeah, I think 49 is for some other different kind of auto features. So let's spend a few minutes on how do we do the quick iteration and the training with data robot, and then I guess we can save time for some of the quick demo and the Q&A. So I mentioned quite a few times we do a very quick iteration with data robot, but let me show you how this works. So there's data robot. This is actually a cloud solution. So you can go to the app.datarobot.com and to start using it. But in order to use it, you have to get access, right? Send an email to Andrew. You can get access for it. So what we do here is we create a project. Creating a project is pretty straightforward in Data Robot. You basically just drag your file. So this is the first screen for creating a project, and all you have to do is create your CSV file into this page, and the project is created. They support other different data sources, which I haven't really used yet. I only use the local file format so far, but that's how you can get it working. So I'm not going to create a project, just in the interest of time. Instead, I'm just using the project I already had in the past, right? So I have a project called feedback, with Yafi with property name, because I clearly label individual property with name, so that I can tell which data point is coming from which auto features. Remember early on, I mentioned there's 29 auto features. So I had to be able to tell out of 3,000 data points, which one is coming from where. Actually, I will show you the data and you get some idea. So show all features. So you can see here, so first I create a special column with a name of 99 and 999. This is actually our target column. And there's a label there to tell you whether it's feedback or echo or normal. For this project I'm showing on Data Robot right here, and also in the wiki page, is actually only feedback detection, because echo is actually, detecting echo is a later effort. So the wiki page doesn't really describe too much about it, but the approach is the same. So in this data set, you see the label only have two, 0 and 1. So it's a binary classification problem. But then all this data point, you can see the AM underscore 7day underscore 94, all this data. So these are actually the individual data point extracted from one type of auto feature called AAM. I forgot what AM stands for. So anyway, it's a name. And then you have ROU. And there's quite a few others. There's a total of 3,361 total features here. So what do we do is that I without knowing which feature is predictive, I don't care, right? I just put all these 3,000 in there, and I just start automatic training with all these models. You can see this on this part now, I already just delete all those models that have bad performance. But when I do the automatic training initially, it takes about 2 days for Data Robot to train about 60 different algorithms in parallel for the 24,000 kind of a training example. It's a pretty big data set with 60 models, and I only have a 4 core. We have a pretty small license with Data Robot. It's only 4 cores. So train about 2 days, but they all go in parallel. And after the end of the day, I'm able to tell which ones perform better, right? Which one have a higher validation accuracy rate. And so I just delete all those ones that had poor performance without writing a single line code or without doing any research, without knowing which feature is predictive. I just did a very first, dirty run with 60 models and all 3,000 data points. And from there, I cycled through. I found it seemed to me is gradient booster tree is good. So I just go with that. And I started experimenting, do feature impact analysis, as I mentioned early on. And from there, I started learning which feature is predictive. So the trick I play here is that I'm able to come down to data. I will show you how to do quick iteration. Let's say you did some feature impact analysis, or your digital signal processing skill set told you the AM is actually is a possible good feature to predict the target state. You can always handpick a few feature data point here, and you can create. You can say test with AM only, for example, right? You can select all the AM data point and say, I only want to test AM to see how good they are. For example, you have a hunch, you think this is actually predictive, right? Yeah, you can create a feature for that. And then what you can do here is that you can create a model just quickly out of here, you can just say, let's say you create a model, you say, oh, probably gradient this booster tree will also work well with a very small data set. So you can just click that, and you're using the one you just created called test with AM only, and you can just add a model. And once you click on that, it started training. Yeah, I'm not writing code, right? So this will probably finish in just about 10 to 20 minutes. And so this is what I mean. You can do really quick testing. And what I do here is that after I do a preliminary feature impact analysis, I quickly come down to a rough idea of what audio feature is possibly have a decent chance to be more predictive, or a combination of them. So I just create quite a few different promising combination tests, put them all together, and throw to data robot, and I do another 4 or 5 rounds of parallel testing. And then within about 30-40 minutes, I'm able to do a very quick drill down from all the way from a 3,000 kind of data set down to 30, down to OBSR only, down to this particular model called a gradient boosted tree. So that's how you do quick iteration and drill down to narrow down your feature selection. So the end result is we found with this our OBSR training with a 112 data point from OBSR feature, and we got it. This is the performance we got. It was gradient boosted tree. Just a quick look of showing you the accuracy rate, the F1 score, the recall, excuse me, the precision. So these are all pretty good to our expectation. And the ROC curve is fairly straight. It's a little surprise, but that's just the way it is. I guess this reflects the fact that for human ears, the pattern is very obvious, right? So there's no ambiguity. So initially we feel this is a bit too good to be true, but after we throw in quite some, actual like the other feedback data we collect from somewhere else, we throw into it, they have a pretty good detection rate. So that's what we have. And anytime, any question for data robot? Where I'm waiting for that, I'm trying to come up with a demo app. Okay. Okay. There's some message from the chat window. Where's the? I wonder if any question on the chat. Oh, okay, that's just yeah, the AM. Thanks, Andrew. Yeah, stand for amplitude. Yeah, yeah, thanks. Yeah, so let's do a demo on the. So we create a very quick Python UI app. Basically, what this app do is to allow you to pick any audio file, right? So we just pick this one. This is a pre-recorded one. You can pick any audio file, and you double click and you can start playing it. But unfortunately, I couldn't quite let you guys hear the sound since I'm on the headset. I just play it. The idea of this sample app is that they will play your uploaded audio, and for every single second, they will make a call to the model to see whether for that past second there are feedback or the echo or not. And we do this on a half-second incremental basis, right? So every single second we detect, and then we move half a second window. We keep doing that, right? So just so that to be more responsive. But unfortunately, if you can hear the audio, I mean, I would encourage you to download the code and do it yourself. But what you will observe is that you will see a very accurate sync. Like when your ear hear the feedback or echo, you will see the application is actually visually trying to show you with the color coding, right? The green background or the red background to show you they detect it. So it's actually, you can see it's actually synced very well. It's just that I use this app to show you how responsive the app can be when they detected the presence of feedback or echo. So that's the demo. I think that's about it. I could spend some time to walk through the Jupyter notebook, which is which is a little bit too detailed, but I probably better save the time for question for Q&A. So let me take a pause here. Any questions? No questions? All right, you guys are really quiet. All right, let me spend some time with a notebook maybe. Yeah. So so the Jupyter notebook is available at the root level of the source project. As I mentioned early on, so we put as I just want a quick walkthrough of this project structure. So at the root level, we have the notebook, and I put a bunch of sample WAV file into the WAV file directory. This is for people to actually, this is not for training, for prediction, for after they got a model, they can use this one to test whether the model is being able to do some appropriate prediction. And on the source, so as I mentioned earlier on, right, we have most of the data, most of the code we write on the source is actually the feature engineer part, extracting data from the audio clip into sample data, into audio features, and not much about algorithm development. And we have a C++ implementation here, right? We have a Python implementation, all kind of implementation here. And then the important data set. So as I mentioned earlier, it's good to actually, it's good practice if you follow the guideline to put a downsample the training data in here, just so people will be able to get on board your project really quickly without asking too much questions. So I highly recommend you guys, all machine learning projects do that, so that I can walk into your project, and play with your data. That'd be wonderful. So with that said, one of the point I want to mention here is that, so I mentioned early on that you can get a quick result with data robot experimentation, but that's not the model, right? That's just the model on data robot. You can't really use it. So, but this is how we leverage the tools. So from data robot, now that we learn this algorithm, it works well with with this OBSR feature, right? That's all we need. What do we do here is that we just go back to the Python code, get started coding. So there's only a few lines of code you have to write, because you don't really implement the gradient boosted tree classifier from scratch, right? So we just use the library from scikit-learn from Python, and yeah, you can see there's like 20 lines of code. You just use that, and you put your training data in there, and you do a fit, which is training. And this way, you just do a retraining without using data robot. You train with on your own laptop, or hopefully in the future we get this AWS and our Google cloud, the machine learning cluster for us, so we can train on the cloud. But those are the pretty easy stuff. So once you do that, then you got your own Python version model, right? You can do the same thing for C++, and that's how we do it. So as I mentioned early on, leverage tools such as data robot to do the most time-consuming part of your project. Quick implementation, come down to accurate prediction, all this stuff. And once you know what you want, you spend maybe just a couple hours to code it, and there you go, you got your project. So yeah, this is the on the Jupyter notebook. This is the only the few lines of code I show you that are actually so-called feature model development, and that's it.
That's all I have. Hey Peter, can you talk about like the hyperparameters of the model? I mean, that you can take some more of the intel you get out of the tool, out of data robot as well.
Oh yeah, good point. Good question, Andrew. I almost forget that. So one thing is, now that you did a training, you know which model you wanted, right? When you actually hand code this, there are some parameters you have to put into the model, and so you don't want to start from scratch on that. So what do we do here is that, so for example, when I created this gradient boosted tree, I have a learning rate of 0.5, features, maximum features, the estimator is 100, the leaf node and all this stuff. So this thing we don't reevaluate this again. So what do we do here? We just copy the hyperparameter we learned from the training on data robot. Actually, how do I get it? I think it's on the advanced tuning. So when you can go to advanced tuning and look at your model parameter right here. So we just learn from here and copy this data into our hand code and do a quick iteration, and there you go. You got your model. Thanks, Andrew, for mentioning this. This is important. So any questions, folks?
Do we have that Jupyter notebook somewhere available?
Yeah, so the whole project is available under the Bitbucket. Is all here, and the link for that is available. We have a project wiki page called Detect Feedback in G2I module. You can search that on the wiki, and this is under machine learning group. And the link for the project, is here. Where to store your data is mentioned on this wiki page as well. Where is that? I think I mentioned the data part. There's a link. Yeah, there's a link for that. That goes through it. Maybe it's on the development guideline. Yeah. Yeah. Okay. Over here. So you put the data over here. You follow this guideline. The onboarding guideline is available as a README file under the project root, the directory. So yeah, so that's all there. Any other questions? Okay, if not, when it's top of the hour now, Wintao, you have any closing statement you want to add here?
Yeah, thank you for guys for coming. So I think hopefully this is helpful to you guys. And again, just like we mentioned in the beginning, I have put the wiki of the BDI Talk in the chat window already. If you have any topics you want to share with the broader engineering community, please feel free to connect with the BDI folks or myself or Peter, or put your topic in the wiki directly. Then we'll go from there. Looking forward to see you guys next time. Thank you.
Yeah, I want to thank you very much for your time to join us. If any question, feel free to reach out to me.
Wenta, will we get a recording of this?
Yes, I have a recording. I'll send it out. I'll put the recording, upload to Wiki, then I'll share the Wiki one more time with the broader audience. Then all the recording will be available for Bangalore, Budapest, Karlsruhe, and US sessions. We have 3 sessions. So I'll be there.
Thank you.
All right. Thank you, guys. See you next time.
Thank you.
Thanks, bye.
Thank you. Bye.